Hi, everyone. I'm Luka, and I'm a quantum researcher in Shane's theory team. And today I'll be presenting you my latest work on verification of delegated quantum computations. The goal of verification is to build more trust in the quantum computers that we aim to build. If a client wants to delegate quantum computation to Quandela, the way that they do it is using Percival. They will be writing a quantum program, which is represented here as a quantum circuit. Send this program to Quandela via the internet. Quandela will run this quantum program on our machines, and we will send back the results to the client. But here the client has no real way of knowing whether the result that we have sent is actually the output of the computation that they wanted to perform. So how is it possible to test that a quantum computer does what it is supposed to do? Well, one technique is to characterize each individual component and perform a lot of tests and trust that once they are assembled, these individual components will work similarly as when they were tested. But obviously, this has a drawback that you need to trust that this composition is going to work as planned. So another way is to test multiple components together. And so you can do this, for example, via performing a full tomography on the system. But in this case, the number of tests scales extremely badly with the size of the system. In fact, it scales exponentially in the size of the system, which means that precisely at the point where the quantum computer is supposed to be performing something useful, you can no longer test it in this way. Another way to do it is to run an application-specific benchmark. This means running a specific application for larger and larger input sizes and seeing at which point this application fails. But this yields no guarantees outside of this use case. So if the client all of a sudden wants to run something else, this benchmark doesn't give anything. And lastly, it is possible to do what's called randomized benchmarking. And Rawad is going to be able to tell you more about this. But it works by performing a sequence of operations and then undoing them with assumptions on the noise model. This gives precise characterization of our quantum device. So the problem with the tests up to now is that they have trust assumptions and they assume, for one thing, direct access to quantum computer, whereas the client might only access the quantum computer via the cloud. Also, it could be that the quantum computer knows that it's tested and performs better on the tests than one after the product has been sold. Even more fundamentally, there are problems which are solved by quantum computers for which it is not possible to test whether the output is actually the correct output from the quantum computation and not simply random. So how is it possible to test that the provider of the quantum computer performs exactly what it says that it will do? This is the core principle of verification, and the guarantee that it offers is that the probability of accepting an output of the computation which is incorrect is extremely low. And the idea for performing verification is to not only perform the computation that you were supposed to be performing, but also mix inside various tests in such a way that the quantum computer does not know where the tests are and therefore cannot pass the tests while failing the computations. As a bonus, since this is done in a hidden way, you can guarantee that the quantum computer and the operator has no information about the computation that is being performed. This is achieved using maximal security available, meaning that we treat the quantum computer as a black box and we have no assumption on how it works. And for more information about these kind of proofs, you can see the one with bars. And the challenge in these verification protocols is to minimize the resources on both the client's side and the server side. So there are various different types of verification protocols. One of them is called prepare and send, where the client will actually have a small quantum device which they can use to prepare single qubits from a limited number of states and send them via quantum channel to the quantum computer. The quantum computer then performs some entangling operation, and then the client and this quantum computer have a classical communication between them to recover the results. Then there are receive and measure protocols, where the quantum computer actually creates a highly entangled state, such as the graph state, for example, and sends the qubits one by one to the client, who can then measure them also in a limited number of bases. Then there are entanglement-based protocols where you don't have one quantum server, but multiple quantum providers, which are entangled with each other. The client only interacts with the servers classically. And finally, we have what is very new research, which is purely classical protocol, where just the client sends classically encrypted information to the quantum server, who then performs quantum computations only on their side. And here the communication and the client are purely classical. So here's an overview of the different protocols. And regarding the security of these protocols, we can see that the first two are perfectly secure, meaning that it is guaranteed that nothing will leak from the computation, and the output is correct up to a negligible probability if the client accepts the result of the computation. In the entanglement scenario, it is perfect, but only assuming that there is no classical communication between the servers, which is a pretty strong assumption. Whereas for the purely classical protocol, the security is only computational. In the rest of the presentation, I'm going to focus mainly on prepare and send protocols. And here, the client's device prepares single qubits from either the states, computational basis states 0 or 1, or from rotated states plus theta. I'm not going to go into too much detail about how this works, but essentially these 0 or 1 states here in yellow, after the entanglement operations are performed in blue, isolate the middle qubits here, which then has a deterministic result if measured correctly. And this can be used as tests to perform the verification part. So the main focus of my work is to design tools to streamline the design of the protocols that achieve verification. As a motivational example, here is a graph that can be used to prepare states for a verification protocol in a previous paper. And as a small test, you can maybe pause the video here and try to see what are the computation, where's the computation and where are the traps and what's the overhead. The solution is that the computation is performed only on these 4 green circles. So this whole giant graph state is used only to perform a computation on linear graph of 4 qubits. And the irony is that the title of the paper was Optimized Resource Construction for Verifiable Quantum Computations. As soon as you present something like this, all the experimentalists start laughing and no one takes you seriously anymore. So the idea is to try to make protocols which are more efficient in terms of resource use. And the first thing that we do is try to, as much as possible, trim the fat from future protocol design. The first thing that we do is to construct a very general protocol for verifying delegated quantum computations. What we mean by general protocol is that any prepare and send protocol can be reframed as this general protocol. And this protocol formalizes the idea between this blind mixing of test and computations. So you will have a large graph, which some parts are going to be used for tests, some parts are going to be used for the computation, and these are going to be independent. And tests can now be anything, any computation which has an almost deterministic outcome, which the client knows in advance. And what we do then is that we reduce the proof for verification, which are usually pretty complex and really involved, to categorizing the types of errors which the tests can detect. And these are very simple errors because they are only Pauli errors. And it's sufficient to reason about three types of errors. Either the errors are detected by the tests with high probability, or the tests are insensitive to the errors, meaning that they will not react with high probability, or the tests are corrected, which means that the computation will almost not be affected by these errors. And as you can see, the goal of any verification protocol is to either increase the size of the first set or make sure that the second set and the third set are the same, meaning that the tests should not react to the errors which do not matter for the computation, but they do pick up the errors which might harm the computation. The next thing that we do is to try to decorrelate the design for tests from the rest of the computation and how we perform the rest of the protocol. What we show is that if we have a small computation, or any computation, which can be repeated multiple times, so let's say the client is able to repeat it a number n times, then we can add additional runs of the protocol, which have the same structure as the computation runs, but which will serve as tests. So these additional three graphs represent tests. And then we can mix them with the computation. And now, since all of this is blind, the server, if once it receives each computation separately, does not know whether it is a test or whether it is a computation. And so at the end, the clients can look at the output of the tests, decide based on these whether it should abort or not. And then if it doesn't abort, it can look at the computation and can perform a majority vote on the output, which means that the server, in order to corrupt the computation, must corrupt at least half of the computation runs. But since it doesn't know which ones are computation runs and which ones are test runs, it should corrupt at least half of all of the runs in order to be able to corrupt the computation. But this means that the probability of hitting a test run will be also extremely high. And as we can see, compared to the previous type of traps and tests that I've shown earlier, there is no increase in resource compared to the original computation, meaning that you don't need an overhead in the number of qubits that you can operate on in order to perform this verification procedure. And as a bonus, we compared to the previous protocols, we also are allowed to tolerate a small amount of noise in our computation, which will not trigger the test runs. As a result, with all of this, we have a general toolbox for designing efficient tests, because we're no longer forced to think about the whole protocol as of a single block and try to prove the security of this single block, which can really take a long time and be very complicated. But we can only focus on the three properties that I presented earlier for the tests, and our theorems that are in the paper take care of the rest. This allows us to really speed up our test production and design also more general types of tests. Previously, all the types of tests that were created were single qubit tests. Here, we can consider much more complex computations, which hopefully will catch more errors and therefore lead to more efficient protocols. We make links also to other types of protocols. So as I said previously, the receive and measure and prepare and send protocols have been shown to be equivalent in the recent paper, not by us. But we show that the prepare and send protocols are similar to entanglement-based protocols, and more precisely based on graph self-testing and stabilizer testing. As a result, we have a very large diversity of schemes from which to choose in order to optimize our protocols. And we have actually designed more efficient tests and improve on state-of-the-art protocols, both in terms of security and noise robustness, using these more general tests. So the end goal is to go towards efficient schemes which can be used on our devices at Quandela. This can be done by tailoring really precisely the verification protocols to the hardware capabilities that we have at Quandela. So choosing the different types of base protocols, choosing the different types of tests that can be performed, the different types of communication that we can do with the clients. This will allow us in the end to increase the confidence of our clients in our technology, because they don't need anymore to trust us that we will perform the correct computation. They know that by performing this protocol, it guarantees to them that the output of the computation is correct, and that we will not violate their privacy and extract information about their computations. And an important thing to mention here is that photonic quantum computers have a huge advantage over all other approaches, because they allow precisely for both computation and communication. And this is something which is very hard to achieve otherwise for other platforms. So in the future, I would like to add even more use cases for devices which can be linked together, such as our photonic quantum computers, both in terms of quantum communication advantage, for which papers have already shown that it is possible to transmit the same information, but using less qubits over a quantum channel compared to classical bits over a classical channel. And also in terms of quantum cryptographic advantage, meaning that it's possible to perform some tasks using quantum computers and quantum communication, which are completely impossible to do using simply classical computers. So the main example is, of course, QKD, or quantum key distribution. But another example is our protocols which are based on non-locality, such as the QRNG. But there are many more which can be implemented. Thank you very much. And of course, if you have any questions, you can contact me or drop by my office or meet me in Massy. I'll be really glad to discuss all of this with anyone who is interested. Thanks a lot.